So one of the things we're going to look at next in regards to probability and independence has to do with what's known as a conditional probability. And a conditional probability is basically the probability that one event happens given that another event is already known to have happened. And this right here is the notation that we use to represent what's known as a conditional probability. And that probability right there is basically the probability of B, and that's this here, given that A has already occurred. And that's a lot of what we're going to look at next in regards to probability as well as some different things with independence. So just a quick example here with a two-way table, and we have the variable E here stands for the grade that someone gets from an engineering and physical science course, and the variable L here represents the grade that someone gets is lower than a B. So what we have here as far as the table goes is we have grade levels, which is an A, a B, or below a B. And then we have three different schools that we're looking at here: liberal arts, engineering and physical sciences, and then also health and human services. So the first part of this here is find the probability of L, meaning find the probability that someone's grade is lower than a B. So you can see here that, and put the totals in here for you as well, but you can see here that the probability that someone gets a grade that's lower than a B would be, here's how many students got a grade that was lower than a B, 3,656 out of a total of 10,000 students there. So that's the probability of L. So the second part of this, which is the probability that someone has or someone is in the engineering and physical science classes given that their grade is lower than a B, and this probability here would be 800 out of 3656. So when we're talking about this part right here, given that someone has a grade that's lower than a B, we're essentially just restricting the table to these values right here. So if you notice, there's 800 students in this particular column that are in the engineering and physical sciences school, and out of those 800 that are in that school, this is the total amount for all three schools put together where the students scored below a B. So that would be the probability for the second part. And then the last part here is the probability that someone has a grade that's lower than a B given that they are in the engineering and physical sciences school. So in this particular problem, we're just restricting ourselves to this row of values right here. So if we were to find what's the probability that someone has a grade that's lower than a B for this group, we would say that the probability for that would be 800 out of 1600. So just notice with these last two parts here, just notice that the total is no longer out of 10,000. The total is restricted to whatever it is that whatever group of people we're talking about here in the second part of this conditional probability. So when you're talking about conditional probability, the order matters when you're asking a conditional probability question. So if I take you back to these last two examples here, just notice that the probability for this right here had a different probability than it was for this right here. And the reason for that is because in each of those two questions, we were talking about two different groups of people there. So that's what we're referring to here when we say that order matters. So in terms of conditional probabilities and independence, one of the things that we say is that two events are independent if the following two formulas are true. So if the probability of A given B is equal to the probability of A, and the probability of B given A is equal to the probability of B, then what we would say is that those two events would be independent. So a quick example here, and once again following up with sort of a two-way table look to this, but the question here says, are the events male and left-handed independent? So what we have as a two-way table here is, at the top we have what someone's dominant hand is, whether they're right-handed or left-handed, and then we also have it broken down by gender, whether they're a male or a female here. So if the events are independent, what should be true is that the probability that someone is left-handed given that they're a male. So if given that they're a male, we're talking about just this row here. And if you notice, there are 3 left-handed males. So that's this 3 here, and it would be out of 23 because there's 23 males. The value for that is 0.13, and then the probability that someone is just left-handed is 7 out of 50, because you can see here there's 7 total left-handed people out of 50. And since these probabilities are different, what we would say here is that these two events are not independent. Because if they were independent, then both of these probabilities here would have to be the same. And that comes from these two formulas up here at the top. So that's just something that we could do from a formula standpoint to determine if events are in fact independent. So just some points of note here about probability, conditional probabilities, and independence. So 2 events are independent if knowing the outcome of one event does not give you any additional information about the probability that the other event will occur. We'll take a look at some examples of that in a moment. And just sort of a point of note, just referencing back some things that we've already done. This is similar to a scatter plot that has no association. And by that we mean when you have 2 variables in a scatter plot that are not associated, then what we know is that knowing the value of the x variable, if there's no association, doesn't really help you to predict what the value of the y variable would be. So just sort of some similarities there in regards to some things we've done previously with scatter plots, and then also some things with conditional probability and independence. So checkpoint question here: for each chance process below, determine whether the events are independent. Justify your answer. So take a few minutes and see what you could do with these 3 questions on your own. So for question number 1, it says to shuffle a standard deck of cards and turn over the top card, put it back in the deck, and that's significant for when we're talking about independence, that you're putting it back in the deck. Shuffle again and turn over the top card. To find events A, first card is a heart, and event B is the second card is a heart. So these events are independent, and the reason that they're independent is because since you're putting the first card back in the deck before you choose the second one, what that will basically do is it makes the probabilities for each of those events both out of 52, since there's 52 cards in the deck for both of the draws there. For number 2, it says to shuffle a standard deck of cards and turn over the top 2 cards one at a time. Now this one we're doing without replacement, and since we're doing this without replacement, these events are not independent, because when you choose the first card, the probability for that would be out of 52, but then if you don't put that first card back in the deck again, then when you go to choose your second card, then it would be out of 51. And since those would be different, that would make those 2 events not independent. And then for number 3, there's another 2A table here. And the question says the 28 students in an AP statistics class completed a brief survey. One of the questions asked was whether each student was right-handed or left-handed. The 2A table summarizes the class data. Choose a student from the class at random, and are the events of interest female and right-handed? Would those events be considered independent? So these events would be independent, and the reason for that is because if you first find the probability that a student is right-handed, that would be 24 out of 28. There are 24 right-handed students out of 28 total students. And among the women, there's 18 women who are right-handed out of a total of 21 women. And if you reduce each of those fractions, those come out to both be 6/7. So since both of those probabilities are the same, meaning that since the probability that someone is right-handed is also the same as the probability that someone is right-handed, given that the person that you choose is a female, then we would say that those 2 events are, in fact, independent. So one of the things that we'll get into looking at as we move through some different things with probability in the next section here is we're going to do some different things with conditional probabilities in regards to not just 2A tables, but also some different things in regards to tree diagrams.